Okay, so the last thing I want to cover for this class is another failure criteria, but this one is used more for dynamic ones. Okay, so let's say here dynamic failure criteria. And we did one for the design of a shaft. Okay, I don't know if you remember, but we did that. We did one. Okay, so let's start over here. Dynamic failure criteria. I'm going to put here the title if you want. That would be either easier. Goodman failure criteria. Okay, there's multiple ones. This is probably the most widely used. Okay, so when you have a dynamic loading, generally they would be into one of these two forms over here. Okay, so they would be either fully reversed, which is the one I'm doing first. So what those fully reversed means is that it's going to be oscillating between two values. So with this, we can go from, let's say, this point here, down, up, down, up, down, and so on. And this is the one that is known as fully reversed, which is the one that happens many times on the shafts, no? Because you go from up, down, about the zero line. There's another type of loading that this time, if we do the same thing over here, it will be the stress. This is time over here. So it's kind of the same as the fully reversed, but instead of having a mean stress of being 0, let's say you can come over here. Okay, so from here, this will be the mid-range stress. So sigma sub m, we give the names later on, okay? So basically now what happens is that this one is going to oscillate, let's say, between two values. Let's say it would be between this value here. So this is 3 down. So we need 3 up, 1, 2, 3 over here. Okay, so we have something like this. So over here would be the max value. This will be the minimum value. The distance between this peak and here, so I should select maybe different color, will be sigma sub A. And now I'm gonna put here the meaning for each one of the terms. So sigma sub A is the mid-range stress. Sigma sub A is the alternate stress. Sigma sub M will be equal to max plus minimum divided by 2. And the alternate here, we have a value of sigma max. So this is from the figure. Divided by 2. Okay. Okay, so for the previous or for the reverse, and oops, maybe I forgot to put something here. Sorry for that. So this is the fully reverse. This is called the fluctuating case. Because it's going to fluctuate between a mid-range value. Okay, so for the reverse and fluctuating cases, comma, Goodman came up with the following failure criteria. Okay, so this is important to understand the concept, okay, of what he did over here. So let's see. We're gonna put, the important thing is to understand the figure. So on the y-axis, we're gonna put the alternate stress. On the x-axis, the mid-range stress. Okay, so here you have different lines. They have different names, but I call them all Goodman or modified Goodman, and you will see what I'm talking about. Okay, so this is the figure. Let's put it here. How to construct the Goodman line. Okay. All right, so the way this is done is as follows. Okay, if the alternate stress is 0, what does that mean? That means that if we look at the history of the stress with respect to time, if the alternate stress or the reverse stress is 0 in this case, what will you have? You will have a constant stress. That would be equal to what? That would be equal to the, so if sigma A is 0, okay, this is 0, means you are just left with the mid-range value, no? Okay, so mid-range value, so will be just, this would be just a constant value of the mid-range. But what does that represent? If the load is constant throughout time, this is the same thing as having a case of static loading, no? Yeah, it doesn't change in time. It's like if it was static. So in that case, when is the structure going to fail? Think about steel or aluminum. When is the structure going to fail? This will be based on what? If it's static loading. So now this depends on your theory, but you have here the shear strength relation. Okay, you can assume, or you can say that that would depend on your criteria, but what would be the more, if you want, optimistic case? When is your structure going to fail? Johnny, you will say that it will fail when you are here on the ultimate, no? Or you could say it's going to fail when you are here on the yield value. But let's say it's going to fail when you are on the ultimate. So you have two choices. Let's say you assume it's going to fail on the ultimate, or you can assume that it's going to fail on the yield value. Does that make sense or not? This is static, no? The static criteria. So in that case, this is going to fail when the sigma m, the mid-range, is equal to the ultimate. So if we look at this curve here, look at the curve here, because this is important to understand, okay? So that means this is going to fail when the sigma mid-range is going to yield either the ultimate or the medium. So let's say we do first the curve for the ultimate. So we have one point here. Let's call this one sigma sub u, and this will be equal to S sub u, because this is what is generally used on the problems. Or if you decide that it's going to fail in yield at the yield value, you will have here an S or sigma sub y equal to S sub y. All right, so this would be the first case over here. So now we do the other case. So this is the static. Now, what happened if actually the mid-range value is 0? So that means what? That now we will be left with the fully reversed case. Okay, this will be the fully reversed. This is the dynamic load, which correspond to the fully reversed stress. Okay, so now that means that we're moving along this line over here. Sigma alternate. So let's say in this case, you're going to assume that, let's say, you are doing like a static case or a very conservative case, that you assume this is going to fail at the yield value. Or let's say you have some data in which you can have, I will define that in a little bit. But let's say you have some data, you have a structure, a piece that you put into an ATM machine and you start shaking, okay, over time. And you leave it over time, you can find out after a certain number of cycles of doing the same thing, the structure is going to fail, no? Okay, and that value is probably going to be lower than the yield value. Does that make sense or not? This is static loading. You can take the load or to this case here, and from here we'll start deforming. But let's say that you go just the mid-range, but you apply this load 1,000 times. This is still going to make the structure to fail or to break. All right. So you can have here an endurance stress. Let's say will be here. Sigma sub E, S sub E. And if you want to put here, sigma sub E, S sub E is the endurance stress obtained from SN figure. What does SN stand for? Stress versus cycle. So for example, okay, you have a structure that should be to a load. I mean, if you do that on a logarithmic scale, it's going to give you a straight line, but otherwise it will give you a line like this. So meaning that if you apply the load only once, probably it's going to break at the yield value, no? If you apply the load multiple times, it's going to apply. So this is T, or let's say N. This is stress versus the number of cycles. So S stress and number of cycles. So this is only to show that if it is one cycle here, probably this value here will be equal to the yield value. And then if you apply this multiple times, probably will start breaking from under the yield value, no? Yeah? Okay. So as you can see, what he did is not that complicated, but then he has this curve. And what he said basically is that, okay, now if I create this line over here, so let's say from yield to yield. So it's different options over here, and they all have different names, but I don't like to give different names. So this is one choice, or I could join this one to the ultimate, okay? But since I don't want to do too many curves, the other case I'm going to take is from the endurance to the ultimate. So this would be two lines. So really the Goodman line is this one here. But I mean, this will depend on your criteria. I mean, if you decide to draw this line over here, it's fine. All right. If you decide to load this one, it's fine. So if you want, you could call this one here, modify. It has a name, but it's not important. Modify Goodman line. So you could take this one here. Maybe let me use different stuff. Let's say it will be with crosses. Okay, and another modified Goodman line could be what? Could be to go from this one to this one, or from this one to this one, no? But I don't want to do too many figures. So in here, without making too complicated, if I use the Goodman line, all right, when will be the structure safe? When would be the criteria to know if it's going to fail or not? So If you stay under the curve, let's say just for the Goodman line, if you stay under the curve, sorry, this is, I say something that is completely the opposite. This is safe. And if you are on top of the curve, it's going to fail. But this is for the Goodman line. If you were using the modified Goodman line, what would it be? On this part, it will fail. On this part, it will be safe, no? Okay? So, I mean, let me try to Google it for a second. All right, so if you go through the different points, if you go, let's say, from the endurance to the ultimate, is called the Gerber, failure criteria. If you go from the endurance to the yield, is the Soderbergh failure criteria. Okay, but you see, they all mean the same thing. If you go from the SE to this one, but using an elliptic curve, is the ASME elliptic curve. If you use from the SE to the ultimate value, is the elliptic. If you go from the ultimate to the fracture case, which is actually when it breaks even past the ultimate, is called the Mora one. But basically, you see the idea, no? All of them, if you are on the lower side, you are safe. If you're outside, you are the structure will fail. Okay, so we're not going to go every single case. We're just going to do the one for the Goodman line. All right. Okay, so as you saw on the Google page, you have different lines that will give you different criteria. But let's say, okay, so for the Goodman line, our failure criteria will be alternate stress divided by the endurance stress plus mid-range stress divided by the ultimate stress should be equal to 1/n. When n over here is number of cycles. Okay, and for the modified Goodman line, you're going to have that sigma sub A plus sigma sub M equal to yield stress divided by M. So here, sorry for that, guys. N is not the number of cycles. N is the safety factor. All right, so you got here the same kind of similar equations, curves, and all the different criteria. Okay. Okay, so let's do an example over here. So a 1045 hot roll steel rod undergoes a cyclic loading from a minimum value of 2 KSI to a maximum value to 10 KSI. The rod has a hole at its center with a stress concentration factor K of T equal to 1.7. The yield strength, of the bar, so the yield, let's say stress, is Sy equal 45 KSI, and the ultimate stress is 8.2 KSI. Okay, and let's say the endurance stress is S sub E equal to 20 KSI. So the question is, determine if the road is safe or not. Okay, so over here, what we need to do is what? We need to do a figure, like always, and the data. So let's say we do a little sketch of our road. So what do we know? It has a hole over here in the middle. What else do we know? Let's see. We know that the minimum is 2. The maximum is 10. So if we go back to the equations that we got from the figures before, so this one here, the mid-range stress, sigma sub m is equal to what? Is sigma max plus sigma minimum divided by 2. So this will give you that the mid-range is what? Is 10 plus 2 divided by 2. Wait, hold on 1 second here. All right, so we're gonna need your help over here. So this is 2. So let me do a figure over here to see what it would look like. Okay, so this is, let's say, 2, 4, 6, 8, 10. Oh, 4, 8, 10. Let's say it will be sigma max. This will be the sigma minimum. So this is 10, 2. So the mid-range is 6. Okay, and the value for the alternate will be sigma max minus sigma minimum divided by 2, which would be 10 minus 2 divided by 2, which would be then 4. Okay, so what does that mean? Is that if we're here, this would be our stress, and the alternate would be what? I don't know which color to use, would be the distance from here to here, okay? All right. Okay, so what does that mean? So let's recall what we got on the previous, from the previous page. From previous page. We have that the mid-range stress is 6, and that the alternate stress is 4. Okay, so now taking into consideration the stress concentration factor, K of T was equal to 1.7. We're gonna have, and I'm gonna need your help over here, that the new mid-range stress would be K of T times sigma sub M, and sigma prime A would be K of T times sigma sub A. So basically, you will increase the load by 70%. Okay, so thank you for the calculations. So these were the original ones. Now, for the, with the safety factor, we have these values over here. Okay. So now what we need to do is the figure. So again, it's difficult to do it if we don't do it to scale, but this will be the mid-range. This will be the alternate. So again, we can do one or two curves, but what do we know from the problem? We know that what do we know? We know the ultimate stress is 8.2. So if you want, we can put here S of U equal 8.2. And the yield stress, oops, 8.2. What is the value here? Oh, it's 82, not 8.2. So 82, sorry for that. Otherwise, it will make no sense. So this is here 82. This one is to be bigger than the yield one. 82 psi, and that the yield is 45. So this is 82, and let's say here the yield, so it's a little bit less than half. Let's say will be here, will be the S yield is 45. And what else do we know from the problems? We know that the endurance stress is 20. So we could put here, let's say, endurance stress 20. And if we do the other one, we could put here, let's say, the yield stress will be here as Y. So if we use the Goodman line as we define it, we go from 0.20 to 82. So Goodman line. And let's see, what was this value here? This is 20. This is 45. Okay, so let's see if this works or not. So graphically, because I think that's why we do the figure. If we use the Goodman line, what is the value of the X coordinates? Will be the 10.2, no? So 10.2 should be somewhere over here, no? Let's say. And the Y should be what? 6.8. So according to this, what should be this case over here? It looks like it should be somewhere over here, no? Yeah? So does that mean that the design is safe or not safe? It is safe, no? Okay. So we say safe. What was the equation we had for the Goodman line? Was sigma sub A divided by S sub E plus sigma sub M divided by S sub U equal to 1 over M. So basically this equation here will give us what? The alternate is 6.8 divided by the S sub E, which is 20, plus sigma sub M is 10.2 divided by the ultimate that is 82. And this is equal to 1 over M. So can you please, guys, solve for me for N over here? So this gives you 2.15. So that means that this design is safe by a safety factor of 2.15. maybe we can go add here to the notes because I did not put it, I just realized. In this equation, those two equations here, if n is higher than 1 or equal than 1, if you want, the design is safe. If n is lower than 1, let's say the design will fail. Okay? Okay, so let's say in this case, this corresponds, let's say, point A in figure. So I mean, let's guess that it will be somewhere over here. We know this is safe. And this is the region of fail. Okay, now just by curiosity, okay? Let's say we do the same thing for the modified one. And we might just do the graphical part, okay? We'll see if we do everything. So for the modified one, what is the modified one? Is the one that will go from the yield value to the yield value, okay? So basically we go from 45 over here to 45 over here. Okay, so again, in this case, where will be point A? Let's say it will be 10.2, so somewhere over here, and 6.8, whatever will be again, it should be safe, no? Okay, so once again, I give you this example, but if you go to different, if you go read the textbook, they give you all those different equations here for the different cases. All right. So read the one we call the, I mean, you have these ones, the Goodman, the Soderbergh, the Gerber, and so on and so on. Okay. And the last thing you can do, but this is really an approximation if you don't have the correct data, which is very difficult to get. But I mean, let's go and look at it. Okay. Estimate or estimation of number of cycles until failure. Okay, so in order to estimate the number of cycles, and SN, which is stress versus cycles graph is required. Okay, so before I did it, I did the figure, but let me just do it again. So ascent curve is generally stress versus the number of cycles. Generally, they give you this in a logarithmic for the y and x is logarithmic, so it makes a straight line, but in generally would be something like this, where if you want, the maximum value here will be the yield value or the ultimate value for a cycle of 1, let's say, and then it will reduce for, let's say, n equal to whatever, 10,000 or a million. So for example, for aerospace, this is very important because what happened to the wings? They might not be subjected to very high stresses, but they are subjected to very low stresses. When they are flying, they are vibrating, no? So they move up and down. So you probably never in this area, but you might be acting over this area here at a stress value over here for a very long time. So when you do your design, you need to make sure that even though you are at this stress value, you don't go above the number of cycles of your design, no? Which can be, let's say, a full flight or can be the life of the component that you want. All right. So these curves are really difficult to get. So that's why this is really an estimation. And basically what you do is that you find the stress and you find what is the maximum number of cycles that you can subject your structures to. Okay, you read from the figure. But here there is something else. So just gonna add what happens if you have a fluctuating load. So basically, these curves are created for this type of loading. Which basically are fully reversed. All right, you take an ASTM machine. You have your ASTM machine. You put your component here. Okay, and you move it up and down all the time, and you can record the stresses, no? Okay, but obviously you do that for a fully reversed. If you have a fluctuating load, what does that mean? Fluctuating load is exactly the same thing, but about a mid-range value. So let's say we have 1. So in this case, what do you do? Because obviously you're not going to find a SN curve that will be done with your exact value for the mid-range static load, no? Okay, so this is when generally you do assume your alternate stress to be like a fully reversed and apply a factor of safety. So this is funny, but again, mechanical engineers don't do that often, but if you go to the aerospace industry, there's this book called the FAR, Federal Aviation Regulation. There's one for structures, and for example, they will give you the whole code to design an aircraft wing or the fuselage, and they tell you, if you have this number of loads and whatever, this is apply a safety factor of 1.5 or 1.25, 1.3, whatever, no? Okay, which that safety factor will be doing what? Will be kind of taking into consideration the amount of stress that is added by the mid-range, okay, which is a static one.